here are our objectives for 3.4. Okay, 3.4, we're going to use the rational zero theorem to find possible rational zeros. We're going to find zeros of a polynomial function. We're going to solve polynomial equations. We're going to use the linear factorization theorem to find polynomials with given zeros, and we've got to be able to use Descartes' rules of signs. Okay, just for the record, 1, 2, and 3 we did in Algebra 2. Okay, 4 and 5 we did not. So we're going to spend a little bit more time on these two, even though 4 is not really hard at all. Neither is 5, it's just you've never seen it before. Is that fair? Okay, so rational zero theorem. In Algebra 2, we called it the rational root theorem. Okay, x to the fourth minus 6x squared minus 8x plus 24 equals 0. So we try to factor this with grouping because it's 4 terms, except we are missing an x to the third term, so that wouldn't be good to begin with. Okay, but we got to find all the zeros, all the roots, all the solutions, all the 50,000 things that it's called. In this textbook, it's called the rational zeros. Okay, so we do the factors of the last term divided by the factors of the first term. Do you remember this? So what are the factors of 24? 1, 2, 3, 4, 6, 8, 12, and 24, right? Those are all the factors of 24. And then divide it by the factors of the leading coefficient, which is 1. So the fact of the matter is, if I put all these in, divide them all by 1, I just get all those things, right? Because dividing anything by itself, anything by 1, you just get itself, right? Now remember, I taught you several different ways to do this, but the easiest way that I taught you to do it was to go to the calculator. Okay? I'm going to add a page on mine that's a graph. And I want to say x raised to the fourth minus 6x minus 8x plus 24. What am I looking for when I do this? Thank you. I knew I did something wrong because I know what it's supposed to look like, but thank you. What am I looking for? I'm looking for where it crosses the x-axis, right? I can only see one place that it crosses the x-axis, so I'm going to start there. Okay? Am I positive that it crosses the x-axis at 2? Well, I could do Control-T and look at the table. Now am I positive that it crosses the x-axis at 2? Yes, I don't even have to guess. I don't have to assume because we don't ever do that anyways, right? But I know for sure it crosses the x-axis because y is 0 right there. Okay? So from here to find the other 3 solutions or zeros, because I know there's supposed to be 4. I've got to find the others, so I need to do some synthetic division with this, right? So I've got 1, 0, negative 6, negative 8, and 24. Why did I add the 0? Because there's not an x to the third, right? Okay, so let's do synthetic division with this. Bring this one down. Multiply these two. Write it here and add. 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 This is not a surprise to us, is it? We knew it would be a 0 because our function, the value of the function at 2 is 0. So we knew that this would be a 0, okay? So this is what we have left. Now we got to figure out, I'm trying to find 3 more. I've already got 1 right here. I need 3 more, right? So I kind of got to start over. What are all the factors of 12? Divided by the factors of 1. Well, it's just going to be everything in the numerator, right? So I want to add a graph, I'm going to graph that. Let's see, so x to the third plus 2x minus, oops, there you go again, making me miss this. None of that was totally my fault. X squared minus 12. Where is it crossing the x-axis? Why didn't I see that the first time? Well, I did, didn't I? Okay. It's got a multiplicity, doesn't it? 2 happens twice. And remember, when we look at this one, Control T, how do I know it has a multiplicity? It changes direction, right? It changes direction right at the 2, so I know it happened twice, at least twice, right? So I'm going to go from here, I'm going to keep going. 2. Bring down the 1, multiply, add. Multiply, add. Multiply, add. So my problem is right here. This is what I have left. I have x squared plus 4x plus 6 left. Well, what do you think is going to happen if I put that back in my calculator? Well, let's just check. X squared plus 4x plus 6. Does it cross the x-axis? No, that's why I couldn't find any other roots besides just that 2, right? How many more roots should I have, or zeros should I have? I should have 2 more, okay? I've got to use this to figure out the other 2 roots. How should we go about solving this for the other 2? Yeah, I probably need to use quadratic formula, right? Because I can't factor it. I don't know what multiplies to be 6 and adds to be 4. X equals negative b plus or minus the square root b squared minus 4ac all over 2a. Negative 4 plus or minus the square root of 16 minus 24. Oh, now I see why I couldn't find it. Do you? Negative 4 plus or minus the square root of negative 8 over 2. What happens when we have a negative inside the square root sign? Negative 4 plus or minus. So I bring out the negative 1, take the square root of negative 1 and get my I. 8 is 4 times 2, so I know the square root of 4 is 2, which leaves the square root of 2 inside over 2. All 3 of these terms are divisible by 2, so I factor a 2 out of each one of those terms, and I'm left with negative 2 plus or minus I root 2 over 1, which is just the same as negative 2 plus or minus I root 2. So if we found all of our zeros. So let's write them all to make sure we have them all in one place. Okay? What are my, I can't even spell zeros. What are my zeros? 2, 2, and then negative 2 plus or minus I root 2. Those are my 4 zeros, right? Guys, what if I asked you to write them as factors? Do you remember how to do that? Yes or no? Okay, can I remind you? If this is the 0, this is the number that goes on the outside of the synthetic division. What does the factor look like? X minus 2. So if this is the second 0, what does the second factor look like? X minus 2. Okay? Here's the third and fourth 0. So we have x plus 2 plus the square root, or I root of 2. It's like a 2-parter kind of deal. And I have one more, x plus 2 minus I root 2. See how they're both plus though? Because this one is minus. Okay? So these are my 4 zeros. These are my 4 factors. Can we do another one? Is that okay? Sorry, were you done writing this down? Yes, okay, just making sure. So how many am I supposed to have? Yikes. Right? Because it doesn't cross at all. That doesn't help me at all. What else could I do? Well, this is a trinomial, isn't it? Could I try factoring it? Well, what if I factored out a -1? What's left? Does that help me at all? Do you know what multiplies to be 4 and adds to be -3? Yeah, me neither. That's a problem, isn't it? So we would probably do a u substitution on this problem. You remember when we did u substitutions before? We would say x squared equals u. And we would say x squared minus 3x plus 4. And we could solve this with quadratic formula, couldn't we? Once we found out what our x was, I forgot to write u's instead. U's. Once we found out what our u was, I would plug it back in with an x squared, and then I would have to take the square root of both sides to solve for our answer. Okay? I'm not going to go any further on this just because we've already talked about u substitutions, and we really need to get to the other things on our objectives list. But that I just want you to keep in mind, if something like this shows up, try to factor it. If it's not working with factoring, try a u substitution. Okay? What about solving? Okay, so first of all, using the rational root theorem, rational zero theorem, to find possible zeros. So in this first example that we did, that was this top part only. That's the rational zero theorem. What are the possible zeros for this particular function? Okay, rational zeros, I should say. Okay, finding them. Well, we looked at the graph, didn't we, to find them. This one we had to do a double synthetic division because we knew 2 worked twice. We did the synthetic division twice to get to our trinomial that we ended up solving with quadratic formula to find the other 2 x values so that I could find all 4 of them. Solving them for the zeros right here. So I used one example right here to talk you through the top 3. You okay with that? Linear factorization theorem is a little bit easier than it sounds, for real. Okay? If I tell you the zeros are 4, 2, and -1, can you tell me the polynomial that this came from? Well, the factors are x minus 4, x minus 2, and x plus 1, right? Well, multiply it out. Multiply the first 2 together to get x squared minus 2x minus 4x plus 8, which is actually x squared minus 6x plus 8, right? And then I still have this x plus 1 that I haven't used yet. So I just go It helps if you make the sounds. Okay? X squared times x is x cubed. X squared times 1 is x squared. -6 times x is -6x squared. -6x times 1 is -6x. 8 times x is 8x, and 8 times 1 is 8. So if I combine all my like terms here, I get x cubed minus 5x plus 2x plus 8. Okay? So if I give you the zeros, you come up with the factors and multiply it all together. That gives me a possible polynomial that it came from. Now here's why I say possible. Okay? Hold on just a second. Because up here at the beginning, I might tell you that these are the zeros, but also f of 1 equals 6. 12. Sorry. Thank you. So if I give you the zeros, and we figure out the factors and multiply them all out and get this equation, how can I know for sure if I have the right equation? Well, look at this. F of 1 equals 12. Well, what's f of 1 if I just put it in right now? Because this is a function, right? So if I put a 1 in right now, I get 1 minus 5, which is negative 4, plus 2, which is negative 2, plus 8, which is 6. Well, so right now, f of 1 is 6. How would I make it be 12? Multiply it by 2? So if I multiplied every single one of these functions, or every single one of these terms by 2, 2x to the third minus 10x squared plus 4x plus 16, does that work? What's 1 cubed? So 1 times 2 is 2. What's 1 squared? 1 times negative 10. What's 4 times 1? And then I have 16. So what's 2 minus 10? Negative 8 plus 4. Negative 4 plus 16. Don't they equal 12? So this is a possible function for these zeros, but then they're going to give you a qualifying statement. F of 1 is 12. F of 2 is 17, or something like that. It's going to tell you a function value. So you have to figure out from the initial function, what do you have to do to make the actual function that they actually want? That's the linear factorization theorem. Okay? Now the trick comes when they tell you the zeros are 4 and 2i. Well, you have to remember back to complex numbers, either from what we already learned this year or from back to Algebra 2, to know that if you have one zero of 2i, you automatically have another one. What is it? Negative 2i. It's not going to tell you that one. You have to remember that it's there. So how many zeros does this one actually have? It actually has 3. It's only going to give you 2. You have to remember about this complex conjugate here. Okay? So when you go to write your factors, you have x minus 4, you have x minus 2i, and x plus 2i to multiply out. Does that make sense? So don't forget about that complex conjugate one. If it tells you an I value, you've got another one. It might tell you you have 4 and negative 3i. Well, then you automatically know you have another one where? Positive 3i, right? Does that make sense? Okay. How are you feeling about the linear factorization theorem to find polynomials? You okay with that? So, Descartes' rule of signs is the last thing we have to talk about today. Okay? So we're going to start off with the function. F of x equals 3x to the 7th minus 2x to the 5th minus x to the 4th plus 7x squared plus x minus 3. Okay? Here's Descartes' rules of signs. Okay? Number 1, the number of positive real zeros of f is either the same number of sign changes or less than the number of sign changes by a positive even integer. So what the heck does that mean? Well, we got to figure out the number of sign changes first. Okay? So if I'm looking at this polynomial that I gave you to begin with, how many times does it change signs? Well, this term is positive. This term is negative. So is that a sign change? So there's one sign change right there. This term is negative. This term is negative. Is that a sign change? No. This term is negative. This term is positive. Is that a sign change? Positive to positive, positive to negative. That's a sign change. So how many sign changes are there? 3. Or less than that by a positive even integer. What's the most popular positive even integer? 2. Yeah, 2. So what's 2 less than 3? So the number of positive real zeros is either 3 or 1. Does that make sense? Number 2, the number of negative real zeros of f is either the same number of sign changes with f of negative x or less than that, less than the number of sign changes of f of negative x by a positive even integer. There's one more thing we have to write under this one because it's kind of specific for this one. If f negative x has only one variation in sign, then f has exactly one negative real zero. So I don't know if you can tell colors very well, but I used red to talk about positive real zeros. Okay? I'm going to use green to talk about negative real zeros. Okay? So the number of negative real zeros of f is either the same number of sign changes when we have f of negative x. See how this is just f of x? It's just whatever it's there. Well, we have to find f of negative x. Okay? So I have 3 times negative x to the 7 minus 2 times negative x to the 5th minus negative x to the 4th plus 7 times negative x squared minus x minus 3. Guys, what happens if I raise a negative x to an odd power? I've got 7 negatives, right? 7 negative x's. Well, those two are going to make a positive, those two are going to make a positive, those two are going to make a positive. What am I left with? A negative x, right? So this is going to become a negative 3x to the 7th. What happens when I raise it to an odd power? It changes the sign. So plus 2x to the 5th. What happens when I raise it to an even power? If I have 4, these two are a positive and these two are positive, right? So it's going to stay the same sign that it was before. What happens when I raise it to an even power? It's going to stay the same sign that it was before. Then minus x, then minus 3. So now we have to count the sign changes again. Okay? From negative 3 to a positive 2, is that a sign change? Yes. Positive to negative, is that a sign change? Negative to positive, is that a sign change? Positive to negative, is that a sign change? Negative to negative? No. So how many sign changes do I have? 3, 4. 4 sign changes. So I either have the same number of sign changes when I do f of negative x, or less than that by 2. So I either have 4 or 2 or 0. However many sign changes I have, I subtract 2 until I can't subtract 2 anymore. Does that make sense? Okay. So that's Descartes' rule of signs. What questions do you have about these objectives? And I know you always tell me the same thing. We don't ever have any questions when you're done. We have questions when we start working. Okay. Guess what you do then? Just ask. Yeah, for sure. Okay. You ready to go? All right. Mark, set, go.